let's take a look at this example problem. And when we were back in statics, we looked at this and we calculated the centroid of this section. We found that the centroid was 11.5 inches from the bottom. So when we calculated that centroid, we measured it from the bottom of the steel. And we found that the centroid of the section was at this location here, where we have y bar equal to 11.5 inches. Now, I'm going to work this problem out. I'm going to do it on the next slide, but let me define a couple of things first. I'm going to define the channel as section number 1, subarea number 1. I'm going to declare that the W shape is subarea number 2. Now, in the last example we did, in the example we did last week, we're working with a primitive shape, or we're working with a channel, and each of the subareas was a primitive shape. So each of the subareas was a rectangle, or maybe you could have a different one where each of the primitives is a circle or something like that, or a triangle. In this case, the subareas are complex shapes, but since we know the properties of those complex shapes, we can use it like that nonetheless. So let me go ahead and expand on this just a little bit. I did a little bit of math up front. Where was it at? Here it is. Okay, so what I'm going to do is I'm going to break this out, and I'm going to sketch the channel. So the channel is like this. All right, maybe not drawn to scale, but close. Well, not drawn terrible. Let's put it that way. And then I'm going to have the I shape, which is, it's an I shape, it's really W section. Like that. And let me come over here and try and do that with some precision. Right, like that. Okay, great. Then here as well, I'll sketch in this axis here. So that is going to be my capital axis. This is a Z, so I could call it the capital Z axis. How do I make a capital Z? Do I put like little things on it like that? It looks kind of strange. Let's just call it the X axis. Even though it's the Z axis, I'll call it the X axis. Then here we have the centroid of the channel. So that's centroid 1. So that is the little X1 axis, and then here we have the centroid of the W shape. That is the little X2 axis, like that. So what I can do then is I can look up the values that I have for these, and I can figure out where these centroids are at. So I don't know if you guys can hear that mower or not, but it is loud and annoying. All right. So what I'm going to do is I'm going to go up to the top of this thing, and let me skip ahead a couple of slides and you'll see why in just a second. So I have these properties tabulated. So for the W shape, we're looking at a W 18 by 50. So we're looking at these properties here. And the depth of that W 18 by 50 is 18 inches. Okay, so let me go back a couple of slides. Apologies for skipping around on you. Whoops. There we go. So that is 18 inches like that. Now, I also need to get up to the top of this channel. So I need the thickness of the web of the channel. So let me see, where am I at? There we go. So if I go here and look at the channel, we're looking at the C10 by 20. So that's this row right there. Actually, might have been smarter. Control H. I can get a highlighter in here, I think. There we go. So that's that row there. Okay, and then I'm actually looking at the thickness of the web. There we go, pen. There we go. Thickness of the web is 0.379 inches. So if I go back, this value here is 0.379 inches. And then I need this dimension here to this green line. And once again, we go back here. That dimension is going to be tabulated here as X 0.606. Okay, so that's 0.606. So I write 607. Why wouldn't I write 607? Because I don't know why, because that's just how my mind operates. So this dimension here, then if we were to work that math out, is 17.78 inches. Over here, it's just half the depth of the section, so that's 9 inches with some precision like that. All right, now let me do one more thing before we leave this slide. I'm going to go in and I'm going to figure out the moment of inertia I sub x2. I can tabulate that, or it is tabulated rather. So let me go to this slide where we have I sub x is 800. And then when we look at the channel, I want the moment of inertia about the y-axis from the table. So I want this moment of inertia 2.80. Why is it the y-axis? It's because this thing is rotated by 90 degrees in our other view. So I need to interchange the axis as it's tabulated here with the axis the way that I have it tabulated in my drawing. So moment of inertia here is 800 inches to the fourth, and the moment of inertia here, I sub x1 is equal to 2.80 inches to the fourth. Finally, the area here, A, I have it written down, is equal to 5.87 inches squared, and the area here, A, is equal to 14.7 inches squared. And now, no shit, they're actually mowing the other lawn. It's not just one guy that mowed one lawn to the left of my house and then went across the street. It's actually two separate lawn care companies that showed up at the same time during class to mow grass. Evan, did you arrange this? I think that would be just the kind of thing you would do. All right. So, Lucia, I see your question. I'll come back to that before we close for the day. It's supposed to, oh, maybe that's why they're all coming in, because, yeah, that could be. Okay. Yeah, I need to get outside. I'm going to go out for a run or for a bike ride or something after class. I get cooped up in this office of mine, and it's horrible. All right. So let me do this. See if I have enough room to work this out here. I'm going to say that I sub big X for sub area 1 is equal to I sub little x for sub area 1 plus A times D squared. And that's going to go up there. All right. So that's going to be equal to, so sub area 1, that was 2.80 inches fourth plus the area. That area is 5.87 inches squared plus the distance, D. And I left one value out of here. This value here is 11.5 inches. So when I calculate that distance, it's going to be this distance here. This is going to be the distance D1, and this is going to be the distance D2. So down here, I'm going to take, this is going to be 17.78 inches minus 11.50 inches. So that's equal to 2.80 inches fourth plus, this works out to be 231.0 inches fourth, and then we end up with a net of 233.8 inches fourth. Okay, and then I'll do the second one. I get, the windows are popping up on me when I try and write down here. That's a problem. I'll just, okay, I think we all right, here we're going to have 800 inches to the fourth plus A. A is 14.7 inches squared times the distance, and the distance now is going to be 9. Oops. I'll go this way. Oh, no, right. 9 inches minus 11.5 inches. And that's squared, that's squared. And then this number works out to be, let's see, it's 800 here. And then here it's 91.88. And then this number works out to be 891.9 inches to the fourth. Now we can add those two numbers together, and we get 1126 inches to the fourth. All right. Now, a couple of things that I should highlight before we move on. It's interesting, the contribution of this equation. So we have the parallel axis theorem where we have the moment of inertia of the section about its own centroidal axis, and then the AD squared term. So this channel, when you bend it about its weak axis, when you bend it about the little x1 axis here, it isn't very stiff. It doesn't have a whole lot of resistance to bending. But when you take that and you move it up by a distance of 17.7 minus 11.5, and you square that distance, the second term in the parallel axis theorem actually makes its contribution to the overall moment of inertia much greater than it would have been if it were located at the centroidal axis. In the second term, though, the moment of inertia of the W shape by itself is already pretty big, and we're not moving it too much. We're not moving it 6.2 inches. We're moving it 2.5 inches. So the second term doesn't contribute as much for the W section as it does in the first section. So it's interesting. It's kind of an abstract idea, but as you work through a lot of these problems, not just in this class, but through subsequent classes in your academic program, you'll develop a greater understanding of that and where some of the local moments of inertia don't contribute as much as the others. So anyways, bottom line, final answer, 1,126 inches to the fourth when we bolt the channel to the W shape like that.